Yes, friends, welcome once again to the class and welcome once again to the channel. And let's look at our topic of today, which we were already learning about the nuclear shell model, and we had come up to here that we had reached up to here, right? Predictions of shell model. Now, amongst the predictions of shell model, we had already learnt about stability of closed shell nuclei or magic nuclei, and this was our point number one. And the point number two was as follows: that shell model is successful in predicting ground state spin and parity of a large number of nuclei. This we had already learnt in the previous lecture, and the case number one we had already learnt. Now we are going to move on towards our case number two. Okay, we are going to move on towards our case number 2. What is our case number 2? Suppose the atomic mass number A, let us suppose that the atomic mass number A of a certain nucleus, okay, the atomic mass number A of a certain nucleus is suppose odd, then what will happen? So the atomic mass number A will be odd. So suppose we have atomic mass number A written over here, then how we can write it? We can write it to be equal to Z plus N. Okay, so atomic mass number A is the sum of total number of protons and total number of neutrons, that is total number of nucleons. So atomic mass number A equal to, this is what? This is number of protons. Okay, this Z is what? Number of protons, and N is what? It is number of neutrons. Okay, and when you add the number of protons and number of neutrons, you get the atomic mass number A. This is what? This is atomic mass number. Okay, atomic mass number. Now, if the atomic mass number A is suppose odd, this number is suppose odd, then what are the combinations that are possible? What are the combinations that are possible when atomic mass number A is odd? So it is quite obvious that if the number of proton is suppose even and if the number of neutron is suppose even, then what will happen? E1 plus E1 will be equal to E1. Okay, so the odd atomic mass number A is possible only if either Z is even, N is odd, or either Z is odd, N is even. Okay, only in this particular case, look at this thing particularly, look at this thing carefully. Okay, let me put this to the upward side and we will learn this. See, the atomic mass number A is odd. Okay, so as the atomic mass number A is odd, so either even Z or odd N or odd Z even N, two cases are possible. Both of them being even is also not possible. Okay, Z plus N. So if suppose Z is even and N is even, then what will happen? The atomic mass number A will be also even, because E1 plus E1 is always even. Okay, and if suppose Z is odd, then what will happen? And N is also odd suppose, then what will happen? Odd plus odd also gives even number. Odd plus odd is also even, right? So only two cases are possible if we want this atomic mass number A to be odd. If we want this atomic mass number A to be odd, then only two cases are possible. That if this is even, then this must be odd. Okay, then this must be odd. Only then the sum will be odd. And the vice versa. Vice versa is also true. If this is odd, then this must be even. Only then odd plus even will be equal to odd. It will be equal to odd. Okay, so this is the thing which you must take care of. So clearly you can see this thing over here, that the atomic mass number A is odd, then it can be either even Z odd N or odd Z even N. Only then the sum will be odd, because even plus odd is odd and odd plus even is also odd. Okay, so this is the situation which is possible over here. Now let's look at this further. If a subshell contains even number of nucleons, if a subshell suppose contains even number of nucleons, then what will happen? So let us suppose that the number of atomic mass number A is what? Atomic mass number A is what? Let me tell you. Even number of nucleons. Okay, and the total number of nucleons is what? It is atomic mass number A. Number of nucleons is what? It is atomic mass number A, right? So suppose the subshell contains even number of nucleons, that is the value of A is suppose E1, then what will happen? Their total angular momenta, okay, their total angular momenta add together in pairs to yield zero angular momentum. Their angular momenta add in pairs according to Pauli's exclusion principle, which I had already told you in the previous lectures, that suppose we have such a situation, the nucleons are being filled like this. So if the number of nucleons is even, for example there are 6 nucleons over here, so the number of nucleons is even, so what will happen? The angular momenta will add together, okay, the angular momenta of this and this will add together to yield 0 because they are oppositely spined. So what will happen? The angular momenta will yield 0 total angular momentum. Similarly these two are also paired. So what will happen? It will yield total 0 angular momentum, okay. So it will yield 0 angular momentum. Just a second guys, just a second. So we had already seen this, that when there is even number of nucleons, then what happens? Suppose there are 6 nucleons, then you can clearly see this thing, that the oppositely spined nucleons are being paired up, and as the oppositely spined nucleons are being paired up, so what is happening? It is yielding you 0 angular momentum, okay. However, if one or more nucleon is added, so what will happen? Suppose I add one more nucleon over here. So what will happen? Then the total number of nucleons will be 6 plus 1, that will be equal to 7. So what will happen in this particular case? If one more nucleon is added, it does not disturb pairs, as pairing interaction is fairly strong. So clearly if this extra nucleon is added over here, then it will not disturb the pairing of all these nucleons, okay. But if we keep on adding more nucleons, then it might disturb, okay. But if we add a single nucleon, the pairing interaction between these is very strong. So addition of a single nucleon will not disturb these pairs, okay, these 3 pairs, because the pairing interaction is fairly strong. So it is written over here that if one or more nucleon is added, it does not disturb pairs, as pairing interaction is fairly strong, okay. Thus the total angular momentum of the single odd nucleon in the highest energy occupied subshell, you can clearly see this over here, look at the laser pointer, okay, you can clearly see this thing, that this is what? This is single odd nucleon, okay, and it must be in the highest energy level subshell, and it is there in highest energy level subshell obviously, because when we fill up the nuclear configuration, the highest energy levels are filled in the last, okay. Highest energy levels are filled in the last whenever we fill the nuclear configuration. So the single odd nucleon in the highest energy level subshell will be responsible for nuclear spin. So this nuclear spin is on account of this particular nucleon only. These 3 nucleons do not contribute to nuclear spin, because those 3 are paired up. Paired up, okay. So nuclear spin I is equal to what? Value of the quantum number J for that subshell, okay. This particular subshell, you can see over here, for this particular subshell, whatever will be the value of J, that will be the value of nuclear spin, okay. So this odd nucleon 6 plus 1, that is odd nucleon which was single, okay, which was not paired up, that is responsible for nuclear spin, okay. And the value of nuclear spin I will be equal to value of quantum number J for this particular subshell, which I am marking in yellow color, okay. This yellow colored subshell, whatever will be the value of J for this yellow colored subshell, that will be equal to the nuclear spin I for that particular nucleus, because only single unpaired nucleon was there in that nucleus, okay. So hopefully you got this, and this we have already learnt also, but for your revision purpose I wrote it over here, okay, for your revision purpose. So still we haven't moved to this particular case, okay, still we haven't moved to this particular case. This point number 1 has been written, that what happens if this is even, what happens if this is even, it is written over here, okay. And odd situation arises, odd situation arises. When does odd situation arise? Odd situation arises when, odd situation arises when you are what we can say, odd situation arises when the number is one more than even number. So as already drawn over here, 7 is a odd number, okay, 7 is a odd number. So 1 2 3 4 5 6 7, okay. So you can clearly see this thing, that these six are what, they are paired, these 6 are paired. And this single one over here, what is it? This single one over here, it will be responsible for the nuclear spin, and whatever will be the value of J for this particular subshell, okay, that will be equal to its nuclear spin. So that is the thing. So we learned that. Now parity of odd A nuclei, okay, what is the parity of odd atomic mass number A nuclei? Parity of odd atomic mass number A nuclei is just parity of odd nucleon, okay, that odd nucleon which I had drawn multiple times. Let us draw it once again. Let us draw it once again. So 1 nucleon, 2 nucleon, 3 nucleon, 4 nucleon, 5th nucleon, 6th nucleon, and 7th nucleon, okay. So this is what, this is odd nucleon, okay, which is unpaired. And the atomic mass number A for this will be odd. Why the atomic mass number A will be odd? Because the total number of nucleons is what, 7, okay. So you can see this thing. So parity of odd A nuclei is just parity of odd nucleon. This particular odd nucleon which is there, you can see this thing, that this is what, this is your odd nucleon, okay, this is what, odd nucleon. So the parity of this complete nucleus, will have a parity which will be the parity of that odd nucleon, this particular odd nucleon, okay. Since nucleon moves independently, already I have discussed that it is single particle model, okay, single particle model. So what happens, since the nucleon moves independently, nucleon moves what, it moves independently because of single particle model, as already discussed in the previous lectures. Since nucleon moves independently, nuclear eigenfunction is product of eigenfunctions of nucleons. So because the nucleons move independently of each other, none of the nucleon is dependent on the other, each nucleon is moving independently of another, okay, and it is moving on account of the force of, nuclear force of other A-1 nucleons. This also I had told you. So since nucleon moves independently, nuclear eigenfunction is product of eigenfunctions of nucleon, okay. Your nuclear eigenfunction, if you haven't learned quantum mechanics, then you won't understand this particular concept. But I am also going to teach you quantum mechanics and complete the playlist after some time. But for the time being, just understand this. Since nucleon moves independently, nuclear eigenfunction is product of eigenfunction of nucleons. Whenever some entity, whenever a group of particles is moving independently, then the eigenfunction of that complete entity, that complete group of particles, will be a product of eigenfunction of individual particles, okay. So nucleon, as they are moving independently, so the nuclear eigenfunction will be product of eigenfunction of nucleons, okay. If they were not moving independently, then what will happen? Then this will not apply, okay. If the nucleons are dependent on each other, then what will happen? Suppose the nucleons are dependent on each other, then what will happen? Then in that particular case, the nucleons, the eigenfunction will not be equal to product of individual eigenfunction, okay. That concept will not apply then. If they are dependent, then the overall eigenfunction of the nucleus will not be the product of eigenfunction of individual nucleons in that case, when they are dependent. But if they are independent, then what will happen? The nuclear eigenfunction will be product of eigenfunction of individual nucleons, okay, when they are independent. So this thing you must remember. This we learn in quantum mechanics. So let us see. Since the parity of nuclear eigenfunctions is -1 to the power L, we had already learned this, right? Parity is given by minus 1 to the power L. Already learnt in the previous lectures. If you haven't watched them, then certainly you should go to the link in the description and should start watching from the very first lecture. There you will understand each and every concept very clearly. Okay. So since the parity of nuclear eigenfunction is minus 1 to the power L, paired nucleons contribute. What will they contribute? Because they are paired up. So the paired up nucleons will contribute product of eigenfunctions, right? Nucleons are moving independent of each other. So the eigenfunction of one nucleon is minus 1 to the power L. The eigenfunction of another nucleon is also minus 1 to the power L. So what will happen? The total eigenfunction will be minus 1 to the power 2L. By laws of indices, L plus L will happen over here. So minus 1 to the power 2L and minus 1 to the power 2L. 2L is what? Even. Okay, anything multiplied by 2 is even number. So minus 1 to the power 2L is even. As 2L is even, so minus 1 to the power 2L will become plus 1. Okay, and plus 1 means even parity. Plus 1 means what? Even parity. So only odd nucleon determines parity for odd A nuclei. Okay, clearly those which will be paired up. Okay, see over here. Okay, 1, 2, 3, 4, 5, 6 and 7. Okay, so what happens? Suppose this has what? Minus 1 to the power L eigenfunction. Then this has what? Minus 1 to the power L eigenfunction. Then this particular nucleon has what? It also has minus 1 to the power L eigenfunction. Then this particular nucleon has what? It also has minus 1 to the power L eigenfunction. Then this particular nucleon similarly has that only. Okay. Similarly, this particular nucleon will have what? Minus 1 to the power L eigenfunction. Similarly, this nucleon will have what? This particular nucleon will also have minus 1 to the power L eigenfunction. Then this particular nucleon will have what? That particular unpaired nucleon will also have minus 1 to the power L eigenfunction. Okay. Now, as these are the nucleons in a single nucleus, these are nucleons in a single nucleus and they are moving independent of each other, right? So when you take product of these two, what will happen? It will give you minus 1 to the power 2L. Okay, so it will be equal to plus 1. Similarly, when you take product of these two, what will happen? It will be equal to plus 1. Similarly, when you take product of these particular two, okay, these two, so what will happen? Again it will be plus 1 in a similar fashion. Minus 1 to the power 12 and it will give you plus 1. Minus 1 to the power 12 will come, minus 1 to the power 12 will come, and again it will yield you plus 1. Now these are done. This is plus 1, this is plus 1, this is plus 1. So what will happen? Eventually this will remain. This particular nucleon over here, this particular nucleon over here will remain, because it will remain as minus 1 to the power L. It will remain as minus 1 to the power L. Why? Why will it remain as minus 1 to the power L? Because it does not have a pair. Okay, it does not have a pair. So minus 1 to the power 12 does not come, as there is no pair of it. So minus 1 to the power 12 does not come. So when you try to find out the parity of this particular nucleus, what will happen? It will be 1 into 1 into 1. Okay, because this was minus 1 to the power 12, minus 1 to the power 12, minus 1 to the power 12, 3 times. So it will be plus 1 into plus 1 into plus 1 multiplied by what? Minus 1 to the power L will be there. Okay, so eventually all this will be equal to minus 1 to the power L. Okay, so the nucleus, the parity of the nucleus is depending on this unpaired nucleon. The parity of nucleus is depending on this particular unpaired nucleon. Okay, so that is the thing which you must take care of. So only odd nucleon determines parity for odd atomic mass number A. So only odd nucleon determines the parity for odd atomic mass number A nucleus. Okay, already told to you. Now conclusion. Parity equal to minus 1 to the power L, where L corresponds to the odd nucleon. Okay, whatever will be the value of L for odd nucleon, that will determine the parity. It may be odd N, odd Z. Okay, so you can clearly see this thing, that either the value of N can be odd or the value of Z can be odd. Clearly this thing. Okay, and if the value of N is odd, then what will happen? If value of N is odd, then Z will be even, because we are talking about odd A nucleus. Okay, we are talking about odd A nucleus. So odd will come only when odd N, if N is odd, then Z must be even. because even plus odd only gives odd, okay, and odd z, then certainly it must be even n, then it must be even n, okay. So this is the thing. So if n is odd, then even z, and if z is odd, then even n, okay, then even n. And atomic mass number A will be odd in this case also, because odd plus even is odd, and in this case also the atomic mass number A will be odd because odd plus even is also odd, okay. So the parity will depend on only if whatever may be odd, okay. If number of neutrons is odd, then the parity of the nucleus, okay, let me write over here. If the number of neutrons equal to odd, then parity depends on neutrons, okay. Parity of what? Parity of nucleus. Parity of nucleus depends on neutrons. And if number of protons is odd, then what will happen? Parity depends on protons, parity of the nucleus, okay. So in short, I can say that when the atomic mass number A is odd, then you must look at the fact whether n is odd or z is odd, okay, and decide whatever will be odd. Then you should decide whether to write the nuclear configuration for neutrons or whether to write the nuclear configuration for protons. That you can decide on the basis of whether z is odd or n is odd, okay. So that is the thing. So parity equal to minus 1 to the power L, where L corresponds to odd nucleon. Odd nucleon means either n can be odd or z can be odd. Other one will be even. If n is odd, then z will be even. If z is odd, then n will be even. So we must concentrate on only odd nucleon. Odd nucleon means if n is odd, then concentrate on n. If z is odd, then concentrate on z, okay. And atomic mass number A is overall odd, but you have to write the configuration of neutron and proton. Configuration of neutron and proton must be written separately, right? So the parity will depend on minus 1 to the power L, and only neutron configuration will be written when this number of neutron is odd, and only proton configuration will be written when number of proton is odd. And wherever the last proton goes, in this case the last proton wherever it goes, whatever will be the value of L, that will decide parity, and the unpaired neutron wherever it will go, that will decide the parity, okay. In which L the unpaired neutron has gone, in which value of L the unpaired proton has gone, that will decide the parity in this case, okay. So hopefully it is clear. So where L corresponds to odd nucleon, it may be odd n or odd z. Either n can be odd or either z can be odd, but only one thing can be odd, okay. Only one amongst n and z, okay. Only one can be odd. Only one can be odd. Why only one can be odd? Because if both are odd, then what will happen? If both are odd, then A will become even. If both n and z are odd, then A will become even. So violation of our condition. Our condition is that A is odd. So either n can be odd or z can be odd. Only one of them will be odd. Only one amongst n and z will be odd. Only one amongst n and z will be odd because the atomic mass number A we have in this condition is odd. As soon as you take this also odd and this also odd, then what will happen? The value of A will become even. So it will be a violation of our condition which we have already written over here, odd A nuclei, okay. So it will violate that condition, and we are not studying that condition right now, right? So whenever atomic mass number A is odd, then decide whether n is odd or z is odd, okay. And wherever the unpaired, if n is odd, then just see whether the unpaired neutron goes, And if Z is odd, then just look at the fact that where the unpaired proton goes, and wherever they go, whatever will be the value of L for that subshell where the unpaired neutron or unpaired proton resides, whatever will be the value of L for that subshell, that will decide the parity in that case. Okay, minus 1 to the power L simply you have to do, because what will happen to other paired nucleons? Other paired nucleons will give you a situation of this kind. Other paired nucleons will give you a situation of this kind, which will yield you 1. Other paired nucleons will give you a situation of this kind, which will yield you 1. So the product with 1 is making no sense. Product with 1 is the same number itself. Product with 1 is the same number itself. So that's why parity is minus 1 to the power L simply, because multiplied by 1, various multiplied by 1 will be there, but all those will be useless because multiplied by 1 is meaningless. Okay. Now spin I equal to J of odd nucleon. Okay, that odd nucleon, whether it is unpaired neutron or unpaired proton, whatever it might be. So spin, ground state spin will be equal to the spin of that odd nucleon. It may be odd n or odd z. Okay, so spin, ground state spin of the nucleus will be the spin of that odd nucleon. It may be either n might be odd or either z might be odd, but the ground state spin of the complete nucleus will depend on which nucleon is odd, and if n is odd, then wherever the unpaired neutron goes. If n is odd, then whenever the unpaired neutron goes, that will decide the spin, and if z is odd, then wherever the unpaired proton goes, that will decide the spin. Okay, and spin will be equal to J, value of J, and parity will be equal to minus 1 to the power L. So in this case number 2 is our covered. Okay, case number 2 is what? Case number 2 has been covered. Okay, now we will move on to case number 3, but in the next class. So thank you very much.